In most of the cases, the flow inside pipes and ducts are turbulent flows. As the velocity inside a pipe is increased, the flow becomes chaotic. The turbulent flow is characterized by random and rapid fluctuations of swelling regions of fluid called as eddies. These eddies transport mass, momentum, and energy to other regions of flow, enhancing mass, momentum, and heat transfer. So we can say that the mass transfer, heat transfer, and momentum transfer is enhanced in turbulent flows. In turbulent flow, the eddy motion causes fluctuation in the values of velocity, temperature, pressure, and density. So we can see in this figure that the velocity is fluctuating about a mean value, which is u bar, and the fluctuation is u dash. The instantaneous value of the velocity fluctuates about an average velocity. So this is u is the instantaneous value of velocity, which is the sum of the average velocity plus the fluctuation. Similarly, v is the velocity in y direction, p is pressure, and t is temperature. The entrance region length can be found by these two empirical relations, and we can see that the length of entrance region is less dependent on the Reynolds number. We have already defined what is entrance region and fully developed region, and you may get this detail in my previous lecture of laminar pipe flow. The velocity profile in the turbulent flow is much fuller than a velocity profile in laminar flow. In laminar flow, the velocity profile is parabolic, whereas in the turbulent flow, the velocity profile is fuller or much more flatter. The boundary layer in the turbulent flow is further divided into various layers, in which the first layer is viscous sublayer. In the viscous sublayer, the viscous effects are dominant, and the flow is nearly laminar and streamlined. Above the viscous sublayer, there is buffer layer. In the buffer layer, the turbulent effects start becoming significant, but the flow is still dominated by viscous effects. Above the buffer layer, the next layer is overlap layer. In this layer, the turbulent effects are much more significant, but still not dominant. Above the overlap layer, there is turbulent layer. In this layer, turbulent effects dominate over viscous effects. So turbulent effects are prominent in the turbulent layer. The flow behavior inside each of these layers is different. Therefore, this turbulent velocity profile cannot be defined by a single empirical relation. There will be different relations for each of these layers. The relation for the velocity profile in turbulent flow are based on analysis and experimental data. Now we will define the velocity profile in viscous sublayer. The flow in the viscous sublayer is laminar and streamlined. The velocity gradient in the viscous sublayer remains nearly constant. Therefore, the wall shear stress can be expressed as tau W is equal to mu u over y. After some rearrangement, we can write this equation in this form, where this ratio of tau W wall shear stress divided by the rho density can be replaced by friction velocity, which is denoted by u star. It is sometimes called as fictitious velocity. So by substituting u star into this equation and after some rearrangement, we will get the dimensionless form of velocity profile in the viscous sublayer. So which is u over u star is equal to y u star over mu. This expression is called as law of wall, and it is valid for smooth surfaces. The left hand side of this equation, u over u star, can be replaced by u plus, and right side of this equation y u star over mu can be replaced by y plus. So law of wall can be simplified in this way. Law of wall is applicable in the viscous sublayer. Now we will define the relation for velocity profile in the overlap layer. In the overlap layer, the logarithmic law is applicable, which is defined by this equation. In this equation, k is equal to 0.4 and b is equal to 5, which are constants and determined experimentally. So by putting in the values of these constants, we get the logarithmic law in this form. This logarithmic law is accurate for values. The logarithmic law is accurate for y plus values of greater than 30. This logarithmic law is not accurate in the buffer layer. As you can see here, that law of wall is applicable in the viscous sublayer, whereas we do not have any relation for this buffer layer. But this logarithmic law is accurate in the overlap layer. So this overlap layer starts at y plus value greater than 30. Next we will define the relation for velocity profile in turbulent layer. The velocity profile in the turbulent layer can be defined by velocity defect law. This relation is independent of viscosity, as we have discussed earlier that in the turbulent layer, the turbulent effects are dominant over the viscous effects. The velocity profile in the turbulent layer can also be defined by power law velocity profile. In this expression, the value of n is equal to 7 for most of the practical flows. This value of n increases with increasing the Reynolds number. We can also find the thickness of viscous sublayer, which is the ratio of kinematic viscosity and average flow velocity. Here in this expression, u delta is nearly equal to the average flow velocity. So u delta is the maximum velocity in the viscous sublayer at this point, which is nearly equal to the average flow velocity. Next, I will explain the turbulent shear stress in turbulent pipe flow. The turbulent shear stress consists of two parts. The first part is the laminar component, which accounts for the friction between layers in the flow direction. Mathematically, it is equal to mu times the gradient of velocity. The second component is turbulent component, which accounts for the friction between the fluctuating fluid particles and the fluid body, also called as Reynolds stress or turbulent stress. Mathematically is equal to rho times u dash v dash. The laminar component of shear stress is maximum near the wall. As we can see in this figure, that near the wall, the laminar shear stress is maximum and turbulent shear stress is 0. This is because eddies that are produced in the turbulent flow loses its intensity close to the wall. This is because the eddies that are produced in the turbulent flow are diminished at the wall because of the no-slip condition. But as we move away from the wall, the laminar component of the shear stress decreases, but the turbulent component of shear stress increases. This is because the swirling motion or the eddy motion of the fluid particles. So total shear stress can be found by adding laminar component of shear stress and the turbulent component of shear stress. So next we will add these two components to find out the total shear stress in turbulent flow. The turbulent shear stress can also be written in the velocity gradient form, where mu t is the eddy viscosity or turbulent viscosity, which accounts for the momentum transport by turbulent eddies. So total shear stress can be obtained by adding laminar component and turbulent component, and we can replace this mu by nu, which is kinematic viscosity, and mu is dynamic viscosity. The wall shear stress in turbulent flow is greater than from the laminar flow. This is because the higher velocity gradient in turbulent flow, which is evident from this figure. We have a larger velocity gradient in the turbulent flow as the velocity profile is flatter. This velocity gradient is the rate of change of this u velocity with respect to y. As we can see in this figure that this u velocity is more rapidly changing with respect to y as compared to the laminar flow. So therefore we can say that the wall shear in the turbulent flow is greater than the wall shear in laminar flow. Measurement of pressure drop and head loss is very important in the designing of piping system. The pressure drop is a function of length of the pipe, diameter of pipe, average flow velocity and density, and Darcy friction factor. And the head loss is the ratio of pressure drop and rho g. Darcy friction factor can be found by Cloribrook equation. In this equation, epsilon over d is the relative roughness of the pipe. Another explicit relation for the Darcy friction factor was presented by Haaland, which deviates 2% from the Cloribrook equation. The Darcy friction factor is a function of Reynolds number and relative roughness of pipe wall, which is evident from these two relations. So, what is the relative roughness of pipe? The wall roughness in the pipe is characterized by the equivalent sand roughness epsilon. This roughness in the pipes is due to the corrosion or deposition of salts. This figure shows the walls of a corroded tube, and its wall roughness is characterized by equivalent sand roughness, the height of the sand particles. So relative wall roughness is the ratio of epsilon and diameter of the pipe or tube. The Darcy friction factor can also be found by this Moody's chart. This chart is used by engineers to find out the pressure drop in the pipes for turbulent flows and laminar flows. This straight line is for the laminar flow, which is independent of the wall roughness, and it can be found by a simple relation F is equal to 64 divided by Reynolds number. For turbulent flows, the Darcy friction factor is a function of pipe roughness and Reynolds number. The bottom line is for the smooth pipes, and the line at the top is for fully rough pipes. Pipes made of glass and plastic are smooth pipes, and the pipes made of concrete are fully rough pipes. The Darcy friction factor becomes independent at higher Reynolds numbers and become only dependent on the pipe roughness. There are three types of fluid flow problems that are encountered in the real life. In the first type of problem, we need to find the pressure drop or head loss, and the length, diameter and volume flow rate of the pipe are given. In the second type of problem, we need to find out the volume flow rate when pressure drop, length and diameter of pipe are known. And in the third type of fluid flow problem, we need to find out the diameter of pipe when pressure drop, volume flow rate and length of the pipe are known. These explicit relations for head loss, volume flow rate and diameter of pipe can also be used for piping system design, and these relations are valid in the following Reynolds number range. Thank you for watching this lecture. In the next lecture, we will discuss the minor losses in piping systems.